Okay, partial derivatives. What the heck is it? Well, you're going to do some calculus because the word derivatives is in there, so get ready. So we're going to look at partial derivatives for a function of 2 variables, partial derivative for a function of 3 or more variables, and then we're going to look at higher order partials, like second and third partials. So the question is, when you have a function of 2 or more variables, like x and y, what happens when you hold one still but change the other one, let it move around some? So this is the question they're asking. You change in one of its independent variables. So the answer is you're going to hold all variables constant. The word constant, underline it, because that's going to be your key. Except for one, the one that you're trying to examine what's going on. Then change that one and examine the results. And examine results. And this process is known as partial derivative of f. And then I'll put in parentheses, w period, r period, t period. That's short for with respect to. With respect to the chosen independent variable. The one that you're trying to take a look-see at. Okay? So this I should say this process is known as partial derivative f. It's known as partial differentiation. So I'll kind of put this down here too, partial differentiation. Okay, so how do you do some partial differentiation? I'm going to first give you the limit definition for partial derivatives, because when you took Calc 1, you may have forgotten, it was some time ago, but they first did limits in Calc 1. How come? How come they started with limits? Because derivatives are defined by a limit. That's why you do limits first in Calc 1, in case you don't know. So same thing here. Monday, we did a lecture on limits in this class. Limits for functions of 2 or more variables. Now you're ready to define a derivative, which involve limits. Okay, so here's the limit definition. So I'll put here the limit definition. So if z equals fxy, function of 2 variables, the first partial derivatives of f with respect to x and y are 2 separate functions, f subscript x and f subscript y. Those are the 2 partials. Defined by, so the fx, which himself is a function of 2 variables, x and y, so there's x comma y there, equals, it's a limit as delta x goes to 0 of f evaluated at x plus delta xy minus fxy all over delta x. That's one of the partial derivatives. Well, he's got more than one? Yeah. The other one is fy, f subscript y, which is also going to be defined by a limit. The limit is delta y goes to 0 of f evaluated at x, y plus delta y minus fxy all over delta y. So I want to just show you a little diagram, which will help for Friday anyway. Here's your parent function, z equals fxy. There's the, well, wait, let me do a Calc 1 problem for you. Ooh, that was not pretty. Let's try that again. Nope. So let's just do a Calc 1 picture. In Calc 1, you had y equals f of x, okay? And because it's a function of 1 variable, you just had a single first derivative. That's your Calc 1 picture. And of course, after that, you have a second derivative and you could keep going. But here in Calc 3, it's going to look a little different. You've got a function of 2 variables, x and y. So the parent function here at the top will be this bubble. And then he's got 2 first derivatives, 1 for each of his variables. So you'll have an fx and an fy. Yeah. No, I don't want to talk about second partials yet. Let's just keep it simple. So how do you get these partials? So the key is going to be that, and if I were face to face with you, it'd be easier for me to gesticulate. But if you could kind of look at my face right now. For fx, what you're going to do is you're going to put on a special set of glasses that when you look through them, anything that is y, the variable y, will temporarily look constant to you, like it looks like a 2 or something like that. So you're going to basically hold y's constant when you take the partial with respect to x. On the other hand, if you're trying to find the other partial fy, you're going to put on a different set of glasses where all the x's will look like they're just a pure number, like 2 or something like that. You're going to basically hold x constant. So this basically says it. For fx, you consider the y constant and you differentiate with respect to x. Similarly, to find fy, you consider x constant, and you differentiate with respect to y. Now, you're not ready to do any examples yet, because I don't think you are. I want to do some quickie prep work for you, review from Calc 1. I'm not trying to insult your intelligence. But if you don't understand unequivocally the key Calc 1 derivative rules, you will be completely messed up when you're trying to do partials. Okay, so let's do some Calc 1. Do you remember something called the constant rule? It's just where you take the derivative of a pure number, like 2, d dx of a constant c. What is the derivative of a pure number? Come on, folks.
0.
0, yeah. And you're thinking, well, that's really dumb. Of course I know that. Well, do you? We'll see. Now, the other rule from Calc 1 that I need you to recall is the constant multiple rule. This is a little bit different than the constant rule. The constant rule says, what's the derivative of something that's a pure number? The multiple rule is, what if you had some constant, say c, could be a 2 or a negative 0.5, whatever, and it's multiplying with a function, and you're trying to dx, take the derivative with respect to x, of that product. Well, the multiple goes along for the ride. So you just copy them down, and then you take the derivative of the function, and you're done. So that's the constant multiple rule. So if you get both of these and you're like, okay, yeah, I get that, let's move on. Well, then you're ready to move on, but you got to wear those special glasses I told you about. So here's an easy function of 2 variables, easy because it's just a polynomial. And we're going to find fx and fy, okay? So let's do fx, and what you're going to need to do for me is you're going to put on a special set of glasses where when you look through these glasses, y is constant. Y looks like the number 2, for example. Okay, here we go. We're going to differentiate with respect to x, holding y constant. So the first term is easy. What's the derivative of 3x with respect to x?
3.
Yeah, just 3. Okay, and then there's a minus next. Okay, now we're going to try and partially differentiate x squared times y squared. Be careful. You're holding y constant. So the y squared just looks like some funky number, a multiple. So you just copy down the y squared because you're now using the constant multiple rule, and you differentiate x squared with respect to x. And that's going to be 2x. Plus, now the last term, you're differentiating 2x cubed y with respect to x. So the 2 and the y, I'm going to just copy both of those down because that just looks like some multiple. Remember, y is like some weird number, times the derivative of x cubed with respect to x, which is 3x squared. And then clean this mess up. So your fx, which is a function itself of 2 variables, so as a reminder, I'll put parentheses x comma y, is 3 minus, and it's tradition to put things in alphabetical order. So please rewrite your second term as 2xy squared. Otherwise, I'll dock you points for yuckiness. And then the last term, and when you make it simple, is 6x squared y. And we're done taking one of the partial derivatives. Questions on fx? Okay, let's get the other partial then. So now we're going to get fy. This time you're going to put on a different set of glasses where when you look through this set of glasses, the x's all look like a constant, like a 2. And you're going to differentiate everything with respect to y. So here we go. what is the derivative of 3x with respect to y? Keep in mind that x just is like a pure number through our glasses. So then 3x just looks like a pure number with respect to y. So what does the constant rule say when you're differentiating a pure number?
It's 0.
Yeah. So the first term's derivative with respect to y is 0. Pretty weird, huh? What? The derivative of 3x is 0? Yes. When you're differentiating with respect to y. That's the weird part about this. Now, the second term, minus x squared y squared, the minus x squared looks like a constant multiple, and you use the constant multiple rule, copy down x squared and take the derivative of y squared with respect to y, plus the 2x cubed is a constant multiple, and you're going to multiply that by the derivative of y with respect to y. So what's the derivative of y with respect to y?
1.
1. Good. And so your final answer for your partial with respect to y is negative 2x squared y plus 2x cubed. And you're done. So now you have your first example of partial derivatives. Congratulations. You'll get a chance to do some of your own today. But any questions on this? Pretty easy, right? Until it's not. So we're going to get harder. Don't worry. It's not always going to be this easy. Come on. First, let's do some notation, and then we'll do a harder example where you're going to have to start really getting tested on if you know all of your derivative rules. Yes, indeed. Product rule, chain rule, quotient rule, how to take the derivative of arctan, all that stuff. You need that in this class. Okay, so let's make sure that we know all the different notation that is used to denote partial derivatives. First up, you already know fx. Okay, fine. And if your function is given by z equals fxy, sometimes they'll just use z subscript x instead. That'll mean the same thing. Same thing. Also, using this differential notation, you might see it written as, see this letter D with a melted stem? Yeah, that's a D that isn't straight stem. And yes, it matters. Anytime we're going to do partial derivative notation, the letter D is not going to have a straight stem. Straight stem is only reserved for functions of a single variable. Anytime you're taking derivatives of functions of 2 or more variables, you will use the melted stem. It's sort of the stem of the D is kind of curved over, like somebody melted it. So you're going to have d fxy dx, and get used to writing these D's, because on your handwritten work, if you neglect to use the proper notation, I will dock you points. Yes, it matters. And then df dx is another way to denote the first partial. And then you might even see it as dz dx. And we already saw that it could be written acknowledging that if you're working with a function of 2 variables, fx, xy. So the notation for fy, you have zy, or it might be df xy dy, or df dy, or dz dy, or fy xy. Okay, those are all the different ways to say all the partials with respect to x and with respect to y. Now let's do a harder example where it's not as easy to get the derivatives, the partials, okay? Because I want you to see that you're going to have to work a little bit. So we're going to find the 2 partials, only this time our function is this guy right here. X multiplied with this exponential, e to the x squared y power. After we're done getting those partials, we're going to evaluate both of them at a specific point, P. So when you're going to get the fx, which means you're going to wear a special set of glasses and you're going to hold y constant. Y is going to look like a 2. You're going to need the product rule, y. Well, what do you think?
Because it's multiplying to.
Does anybody know why we would need the product rule to take the partial of x times e to the x squared y? You got a product, right?
Yeah.
You got an x times the exponential, right? So you're going to have to do this very carefully. So you're going to first take the derivative of the first factor, x, with respect to x. Well, that's just a 1. And then multiply that by the other factor, plus x times the derivative of e to the x squared y power, but with respect to x. So you remember the exponential rule from Calc 1 that says the derivative of e to the u is e to the u times u prime. That's still going to be true. So you're going to have e to the u, e to the x squared y, times the derivative of x squared y, but with respect to x. So what would that be?
1.
No. What is the derivative of x squared y with respect to x? Remember, you're
2x
holding
y.
y constant, so y just looks like a number, like a 2. And so you would just copy down the 2, and then you would multiply by the derivative of x squared with respect to x. What's that?
Just 2x.
Thank you. This is your u prime for your exponential rule. So you're going to put that right here. I'll put it as 2xy. And then you could clean this partial up so it's a little bit prettier. So I'd multiply these powers of x's together and put the 2 in front. And here is the partial of the function with respect to x. E to the x squared y plus 2x squared y times e to the x squared y. If you want to factor out a common factor of e to the x squared y and rewrite this partial, I'm okay with that. But I'm also okay if you don't do that. So I'm done finding the partial with respect to x. Any questions? Okay, so now let's go ahead and find the partial with respect to y. So this time you're going to put on a different set of glasses and you're going to hold x constant. So x is just going to look like the number 2 or whatever, differentiating with respect to y now. I do not need a product rule. Why not?
Because x is considered constant.
Very good, because x is just like a 2, so you don't have to break out the big guns and go use a product rule. So you're just going to go fy, you copy down using the constant multiple rule, x, times the derivative of the exponential, which is e to the x squared y, with respect to y now. So you're still going to use this exponential rule for derivatives that you learned from Calc 1. So you're going to go e to the u times u prime. So what's the derivative of x squared y with respect to y now? That's a different story, right?
X squared.
Yes, it's just x squared, just the multiple. And then clean this up a little bit to make the fy look a little prettier. So your fy, after I multiply all the powers of x together to get a single power of x, I got x cubed e to the x squared y. And there's my partial with respect to y. Yay. And we now just need to evaluate both of these guys at the point. So to finish this problem off, we got to do a little extra there. They wanted us to evaluate fx at the point 1 ln 2, and you're just going to substitute. That's all. So substituting 1 in place of x's and ln 2 in place of y's. And remember that e to the ln 2 is a nice number. It's 2. So my final answer for the fx evaluated at the point is this weird number, 2 plus, wow, that's really yucky. 2 plus 4 ln 2. I would also accept, for those of you buffs who like to simplify your logs, 2 plus ln 2 to the 4th, which is 2 plus ln of 16. That's equivalent. So either one of those answers is fine. Either way, it's a weird number. Now, what about fy evaluated at the point 1 ln 2? Same thing. You're just going to do some substituting and you'll get 1 cubed e to the 1 squared ln 2, and I just get 2. And I'm done with this problem. Moral of story, partial differentiation is a little bit different from regular derivatives from Calc 1 and 2, because you have to have this idea of holding a variable constant and differentiating with respect to the chosen variable. Now, what about these derivatives values that we got? So back in Calc 1, you know that when you found a derivative and you evaluated it at a point, it gave you the slope of the tangent line to that point. So we have a similar geometric interpretation here in Calc 3, thank God. So here's the geometric interpretation. When you're getting df dx, you're differentiating with respect to x. If you have your surface here, which is this red picture here, so that would be the graph of z equals fxy. It's a surface. If you cut it with a vertical plane right here that's parallel to the x-axis, and you sat on a point right there on the surface. Let me get a different color here because this is getting pretty messy. So let's say you were a skier and you wanted to ski down this mountain, which is given by this surface here, z equals fxy. Let's say you're right there. There's you standing there with your ski poles or whatever. If you were going to ski in the direction of the positive x-axis, the slope is going to be given by this number here if you plug in that point where you're standing. Actually, you plug in the way down below here on the earth, the ordered pair, x naught, y naught. You plug that into your partial, and that gives you the slope on the mountain. Okay. Now, what if you want to ski, same point, but what if you want to face in the y-axis direction? So here's you with your skis, and you want to ski in the positive y direction. No problem. The slope of this mountain is going to be given by the partial evaluated at that point. Now, what the real deal is what, if I'm going to get real nitpicky here, is they draw a tangent line to the curve that is given by the intersection of that vertical plane and the surface. And that tangent line slope is given by these partials. So over here, you've got your surface and you slice it with this green vertical plane, and the intersection of those two surfaces gives this curve, and the tangent line to that curve is going to have a slope in this case too. Now, because this is a positive, at least the Fy is definitely a positive number, so is the X. It means you'd be skiing uphill, not downhill. And in order to ski downhill, you would need your slope to be negative. So neither of these numbers is conducive to skiing. It would be more like rock climbing. I'm just saying. Okay, so let's look at an example here. I'm going to do a quickie, 2 examples, and then you and your buddy are going to try one on the next page. So letter A, based on what we just talked about, what's the slopes in the x and y directions for this surface given by fxy equals negative x squared minus y squared plus 25/8. And then once we're done getting those, we'll evaluate it at the point. Okay, so these partials are pretty easy to get because this is a very easy function of 2 variables. So if you're going to hold y constant and differentiate with respect to x, let's do this term by term. What is the derivative of negative x squared over 2 with respect to x?
Negative x.
How about the derivative of negative y squared with respect to x?
0.
Yeah. And of course, a pure number, 25/8 is 0. So you're just going to get negative x. And then if we evaluate it at the point 1/2, 1, well, what about that z coordinate? How do you plug that in? You don't. That's just giving you the ordered triple on the surface itself. It doesn't help you to get your partials slopes there. So here you're just going to substitute a half for your x. Now this is a negative slope, which is good if you're into skiing, because that means you could ski in the positive x direction since you have a negative value here. You'll be going downhill, not uphill. Fy, if you now hold you hold x constant and take the derivatives with respect to y, what is the derivative of negative x squared over 2 with respect to y?
0.
Negative. Oh,
Sorry. I thought you were talking about the first.
Yeah, what is the derivative of negative x squared over 2 with respect to y?
0.
0, because that looks like a pure number. Well, how come? Because x looks like a pure number, and negative x squared will look like a pure number, and negative x squared over 2 will definitely be looking like a pure number. So we use that constant rule from Calc 1 since we are taking derivatives with respect to y. Okay, so that's done. And then the derivative of minus y squared with respect to y is negative 2y, and then the 25a goes to 0. So you're just going to get negative 2y. And so then when you evaluate this at the point with coordinates of half 1, you're going to get, just substituting here, I get a negative 2. Also a negative slope. That means I can ski in that direction. Now, if you're a hot shot skier, like a friend of mine is, he's skiing right now in Montana. He's really good. Which of these slopes would be your favorite direction to ski if you like slopes that are nice and steep? You like those moguls, you know? Anybody know which one? Should I ski in the positive x direction with a slope of -0.5? Or would I have more fun if I skied in the positive y-axis direction with a slope of -2?
probably.
-2.
Yeah, the -2 is going to be a steeper slope. It's more negative. So if you like skiing, you probably want to go down that direction. If you're like me, who I get scared stiff when I ski, I'm never going to ski again. I skied twice when I was 18, and I pretty much sidestepped down the whole hill, and I cried all the way up the lift. I'm not a skier. But if you are, you want to go with the more negative. Okay, now let's take a look at another kind of easy example, but there's something weird that's going to happen here. So keep your eyeballs out for this for later. Well, when's it going to hit? You know, what do you mean later? When I'm talking about later, I'm going to be talking about like 15:06. You better know what's happening here. So it'll hit you later. So we're going to again get the partials here, and this is a pretty easy function to take the partials of fx. You're going to hold y constant, differentiate with respect to x. So the derivative of 1, of course, is 0, but then the second term you're going to have, using the chain rule, -2 times the quantity x minus 1 to the 1 times the derivative of x minus 1 with respect to x, but that's just 1. And the derivative of the third term is going to be 0. How come? Because it only has y's in it. So it just looks like a pure number. So this derivative just looks like -2 times the quantity x minus 1. Fine. Now you're going to get the other partial with respect to y. So you're going to differentiate with respect to y. You're going to hold x constant. First term looks like a 0. Second term is a 0. Third term, use that chain rule. And so you're just going to get -2 y minus 2. Fine. Now you're going to evaluate this at both of these guys at the point 1, 2, 1. And again, they just gave you the z coordinate because that's the point on the surface. So you're going to ignore it and just substitute in the x and y coordinates here. So here, ooh, I get a 0. Is that possible? Sure. What about fy? Well, I'll plug in the point 1, 2 here. Ooh, I also get a 0. What does this mean? Let's talk about what it meant when you were in Calc 1 so you could get a handle on what it means here in Calc 2. In Calc 1, when you had some, say, function of, let's say this is a graph of y equals f of x. And right here at the peak of a mountain or at the bottom of a valley, do you remember that the tangent lines were horizontal? And so your slopes were 0 at those points? Please say yes.
Yes.
Okay, good. So what does that mean for this? For us, what it would mean is this point 1, 2 either is the top of a mountain like this. So you instead of I mean, you can think of like a tangent line being horizontal there, or, and you're not sure yet, well, how do you know if it's one or the other? Because in Calc 1, we found out it might be the bottom of a valley from the surface. You know, it looks like the bottom of a cup. One of the others that's going to happen. So you either have a rel max or a rel min. One or the other is happening right now. And one way to tell would be to graph this puppy with a graphing system. And the other way to tell is, well, I can't tell you yet. That's later on in this chapter. We have ways of figuring out if you've got a max or a min. Okay, so stick around. But if I were to graph this puppy, I go z equals 1 minus parentheses x minus 1. Nope. Squared. And then minus the quantity y minus 2 squared. Let's see what it looks like. How bad could this be? Oh, it's only showing me a part of it. Whoa. Stop spinning. You're making me dizzy. Okay, I need to go into my view, my parameters. Let's do negative 10 to 10 for x and y. Maxes and mins for the ranges. So we can see this. And I hope you can see that it is looking like paraboloid. Yeah, that looks better. So you can see it's one of those quadric surfaces. It's a paraboloid. Can you tell that it does look like there's a max there? Let me spin it around so it's like that. It's supposed to be a real max. Ha! That's not looking too good. So it's hard to tell what's the top. That is a max right there. It does not have a minimum because it goes on forever, down, down, down. But it's kind of a cool looking surface. Anyway, I always like to figure out what these are. Okay, so I'm done with that. Now you guys are up. So I'm going to have you try finding a partial. I'm purposely giving you something a little bit hard. Not that hard, but I'm testing your knowledge of Calc 1 and taking derivatives using the power rule. So that's your tip before I stick you into breakout rooms. So this function here that you're going to find fx and fy and then evaluate at this point, know your power rule for derivatives. Well, what's the power rule? Well, you know, d dx of x to the n is equal to n x to the n minus 1, right? That's the power rule. I hope you remember that. All right, so I'm going to put you in some breakout rooms. Please turn your mic on so you could talk to your buddies. So it's easier to... Okay, I'll see you in there. Bye. Okay, welcome back, guys. I looked around and most of you were on the right track. I just wanted to remind you, this is our syllabus. Can you see the screen? So quiz 5 is coming up. And notice quiz 5, you still need to know 15.1, so please don't forget that. So, you know, hey, we're getting closer and closer to spring break. You see that? Yay-hoo! Can't wait.
Oh no.
What do you mean, oh no? Bad, Nathaniel? I think that's good, right?
Yeah. That means there's gonna be a lot more work to do.
Well, it's always more work. Now, here's a tip. If I were you, I would have rewritten this function like so. Now, you don't have to, but it helps you when you're going to do the power rule. So I would have rewritten it. And then when you're going to take fx, which means you're going to hold y constant, I heard some of you saying, oh, you set the y to 0. Never set any variable to 0. You're holding it constant. As if not, it's not 0. Okay. Yes, I'm sure 0 is a constant. Yes, that's true. But when I say set it to a constant, that means please don't set it to 0 in your mind because you're going to blow it out. Like set it to like a 2 or something. So your first term, the 1/3 and the y to the -1 look like a constant multiple, and you're going to multiply that by the derivative of x squared with respect to x because you're taking the first partial of the function with respect to x. Plus, and then the 4 and the y squared look like a constant multiple, so just copy it down, and then multiply with the derivative of x to the -3 with respect to x, and then using the power rule, that's -3x to the -4, and then clean this up because I don't like negative exponents. I mean, it's correct, but it's ugly. So you want to rewrite it so it looks a little more pretty with the positive exponents. And then I get, 4 times 3 is 12. Okay. And then you got the y squared over x to the 4th. So there's your first partial of f with respect to x. And if they're asking us to evaluate at the point and you only care about the x and y coordinates. So after you substitute and 6 for x and 1 for y, you should get a very weird number. Well, you get -4 minus 1 over 108. Which is -433 over 108. Ew, that's weird. Very strange. The fact that it's a negative number means if you were facing in the x direction, you'd be going downhill instead of uphill, which means you could at least ski in that direction if you like skiing. The fy, a different deal because now you're holding x constant differentiating with respect to y. So here's your function again. When you hold x constant, the 1/3 x squared is a constant multiple. Multiply that by the derivative of y to the -1 with respect to y, and I get -1 y to the -2, plus, and then your 4 and your x to the -3 look like a constant multiple. Multiply that by the derivative of y squared with respect to y, which is 2y, and then clean this mess up. So after rewriting with positive exponents, so it looks a little prettier, you'll have -x squared divided by 3y squared plus 8y over x cubed. And when you evaluate this at the point with coordinates 6, -1, be careful here. You're going to substitute 6 for x and -1 for y. So that's going to also be some really weird number. What do I get? -36/3. Plus -8 over 6 cubed, which I believe is 216. And then use your frac command on your calculator, and I get -325/27. It's also a negative number, which means you're going downhill if you're facing in the positive y-axis direction. Questions? Everybody okay? All right. So now let's extend this up. Let's jack it up a notch. What do you mean? Well, what if you had a function of 3 variables? Oh, yeah. A little bit different story. So here's a function of 3 variables. What does that mean? Then you'd have 3 partials. You'd have fx, fy, and fz. And the other notation is with the Leibniz notation, if you will, dw over dx. Notice the letter d has a melted stem. So how would you do this? The limit definitions for these would look like this. You take a lim as delta x is varying, or as it goes to 0, f evaluated at x plus delta x, y, z minus f of x, y, z all over delta x. You have that difference quotient again. Here's your limit definition. We're not going to use the limit definitions to find these derivatives, thank God. But I just like you to see them. So for your enlightenment, okay, f of x, y plus delta y, z minus f x, y, z. If you take complex variables, which is an upper division math class, you will thank me later that I'm doing this. Yeah, because in those kind of classes, you write these difference quotients a lot. And if you already have some familiarity with them, then you won't be so scared. So here you have f, x, y, z plus delta z minus f, x, y, z all over delta z. But we're not going to use the limit definitions. But what we are going to do is when you differentiate a function with 3 variables, when you put on that special set of glasses, you have to hold 2 out of the 3 variables constant and differentiate with respect to the chosen variables. So you got to be real careful here. So let's just, we're going to find DFDZ only, even though there are 3 partials total of this easy function of 3 variables. It's just a polynomial. So you're going to hold both x and y constant, not setting them equal to 0, people. Please don't do that. It pains me when people hear something that I'm saying, but then twist it where it means something totally different. And then they totally blow it. Oh, well, you said that. I heard you say it. No, you didn't. Let's replay the tape. So what is the, oh no, I don't want to Skype. Thank you for asking though. What is the partial with respect to z of the first term, x times y?
0.
0, good. Because x and y both look like constants, like 2's. 2 times 2 is 4, the derivative of 4 is 0. Plus the derivative of yz squared with respect to z. So y is a constant multiple, copy it down, differentiate by with respect to z, and you get 2z, we'll clean that up. And then the derivative of xz with respect to z is x, and then clean this up, and you get 2yz plus x. And we're done. How about letter B? This is harder. You're going to still find DFDZ of a function of 3 variables, but it's z times sine of xy squared plus 2z. I claim you need the product rule. Why? You see why?
Multiplication.
Because you've got a z times this function sine that also has a z in it. So you definitely need the product rule while you're differentiating with respect to z. So you're going to hold x's and y's constant still. And then you're going to go, okay, fz is the derivative of the first factor, z with respect to z is just 1, times the other factor. I'm just going to copy it down, sine xy squared plus 2z. Okay. Plus the z times the derivative of that sine function with respect to z. So you're going to use the chain rule. You're going to have cos of xy squared plus 2z multiplied by the derivative of xy squared plus 2z with respect to z. So what's the derivative of that argument for your cosine, but with respect to z? Well, the derivative of xy squared with respect to z is 0. And the derivative of 2z with respect to z is 2. And then clean this mess up so it looks a little nicer. Move this 2 way out in front. I like the coefficients way out in front, please. I'm trying to train my Calc 2 students to do that. And oh boy, it's a challenge. And we're done. So there we use the product rule to find that partial. And now let's kick it up another notch. Oh my God, this is a function of 4 variables. Can we do that? Sure, you can take a partial of however many variables you have. You have to be careful though. They want DFDW. What does that mean? You have to hold x, y, and z all constant and differentiate with respect to w. So what I would do first, because I don't want to use the quotient rule, this function of 4 variables can be rewritten as, that's a comma there, what the heck? I had a student in a Calc 3 class not too long ago. He would not get this notation here. He kept writing like this. And don't do this because I'm going to mark off points. And he kept doing this the whole semester. Oh, X, Y, Z, W, like that. No, 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 no. You got to put commas in between for proper notation. So f, x, comma, y, comma, z, comma, w. I'm going to rewrite it as the quantity x plus y plus z times w to the -1 power. And the reason why I'm doing that is when I differentiate with respect to w, so fw, x, y, and z all look like constants. So that they look like right now a constant multiple, copy it down, times the derivative of w to the -1 with respect to w, so that's -1 times w to the -2. And if I rewrite this without negative exponents, so it looks a little nicer, it's going to look like that. And we're done. There's the partial with respect to w. Now, how many partials total, first partials, does this function in letter C have? Like, here's the parent. How many first partials total does he have? We know he's got FW, so that's 1. 1 of how many?
4.
4 total. Very good. Because you've got FX, which they didn't ask us for. You have FY, you have FZ, and you have FW. You've got 4 babies. 4 babies, because you had 4 variables that you're dependent on. So that means 4 derivatives. Does that make sense? So if you had a function of 100 variables, which could happen, how many first partial total would you have?
100.
Yeah. I wouldn't want to be getting all of those, man. Okay, I have a fun little meme for you, okay? So this first character is a constant, because you can tell it's a C, okay? It's a constant, like 2. Oh no, there comes differentiation. And you know a constant, when differentiated, goes to 0. And then the e to the x guy says, oh, so what? And then the constant says, I'm a constant, it's going to eliminate me. And then the e to the x says, oh, I'm e to the x. Stay with me. I will protect you from differentiation. Because, you know, the constant multiple rule, if you're just trying to differentiate c e to the x, the constant doesn't get killed off and go to 0. So that the e to the x says, as long as you're with me, baby, differentiation can't eliminate you. So this guy is going to take the derivative with respect to y of c e to the x. What do you think that's going to equal?
0.
0. I thought this was pretty funny.
That's
I
pretty
just
good.
got this from the net. Okay, so if
I like that one a lot.
you don't think it's funny, that's okay. You know, maybe you need to go find a sense of humor today. Okay.
This is nostalgic.
I just was thinking that was kind of cute. Now that you know what d dy means, because d over dy means take the derivative with respect to y. Okay, all right, let's take a look at higher order partials and then we'll wrap it up today. So what about higher order partials? Well, in Calc 1, you had second derivatives, third derivatives, fourth derivatives, and all that stuff. And you have the same here in Calc 3, but it gets a little bit crazy because let me just draw you a little schematic here. Suppose you had a function of 2 variables, d equals fxy. Okay, just say. Okay, then what? Well, we already discussed that that means because he has 2 independent variables, x and y, he's going to have 2 babies. One partial for with respect to x, which itself is a function of 2 variables, and the other partial of f with respect to y. So those are your first partials. Okay, but how many grandkids are you going to have? Like how many second derivatives? You're going to have 4. Yeah. So one of them, and I'll give you the notation as we go, is you're going to take the f dx, which we have right here, and you're going to take his derivative with respect to x. Okay, so there's a few ways to denote that. One way is d squared f over dx squared. Another more common way, because it's a little easier, is f XX, where the first letter indicates what happens first. Okay, that's one of the grandbabies. The next grandbaby here is where you start with fx, but then you take the derivative with respect to y. That's this right here. And so that looks like d squared f over dy dx, which is fxy. So that's the other grandkid. Okay, there's two more grandkids, two more second partials here. One of them is where you start with your df dy, your first partial, and you take the derivative of that with respect to y. So d squared f over dy squared is one way to denote it, and another way is fyy. So the other grandkid over here is where you start with your df dy, but you take his derivative with respect to x. So it looks like d squared f all over dx dy, which is denoted fyx. Okay, those are subscripts. Okay, now these last two second partials, which one of them is fxy, that's this guy here, and the other one is fyx. Those guys have a special name. They're called mixed partials because they're kind of a mixture, you know, half x, half y. Okay, so there you go. There's your second partials with the notation and why you have 4 of them. So how, let's go ahead and do an easy problem where we find all of the second partials for this beautiful polynomial function. Very easy to do. So in order to find the second partials, you better go find the first partials because that is order number 1. So fx, I'm going to do this fairly quickly. I'm going to differentiate with respect to x, which means I'm going to hold y constant. So the first term's derivative, 3xy squared with respect to x is 3y squared. The derivative of negative 2y with respect to x is 0 because there are no x factors in that term at all. So it goes to 0 because it's treated as a constant. And then the derivative of 5x squared y squared with respect to x is, does anybody want to do this quickly in their head?
10xy squared.
Good. 10xy squared. And if I clean this up a little bit, you know, you don't need to get the 0. Just don't even bother writing it. It's gone. Okay. So there's one of the first partials. Let's go get the other first partial, fy. So start over and now take the derivative of this z equals fxy, but with respect to y now. So the derivative of the first term, 3xy squared, with respect to y is, you tell me.
6xy.
6xy. And then minus the derivative of 2y with respect to y. Well, it's just minus 2. And then plus the derivative of 5x squared y squared, but with respect to y. Okay. Now let's go get the grandkids, shall we? So we have the first partials. We're done there. Now let's get all 4 of the grandkids. Just making room here. Okay, first up, fxx. What's that? Well, the first letter tells you who you're operating on, which means fx. Okay, so take his derivative with respect to what? And the second letter tells you with respect to. So you're going to take the derivative of fx with respect to x. Okay, so what's the derivative of the first term? 3y squared with respect to x.
0.
Plus the derivative of 10xy squared, but with respect to x.
10y squared.
So this guy is just 10y squared, right? We're done with fxx. Let's go ahead and do fxy. fxy, the first letter tells you where he came from, that's fx. The second letter tells you what you're going to differentiate with respect to. So we're going to differentiate wrt with respect to y. So look at fx again, there he is, and take the derivative of him with respect to y. So the derivative of 3y squared with respect to y is?
6y.
6y. How about the 10xy squared with respect to y?
20xy.
So we're done with fxy, and now let's move on to the other 2 grandkids, fyy. Fyy means go look at fy, which we got, but take his derivative with respect to y. So the derivative of 6xy with respect to y is 6x. And of course, the derivative of -2 goes to 0, so we won't even bother writing it down. And then the derivative of 10x squared y with respect to y.
10x squared.
So there's fyy. And then now let's go get fyx. So fyx is going to be where you look at fy again, but you take his derivative with respect to x. So start over. What is the derivative of 6xy with respect to x?
6y.
Yeah, 6y. Plus, because the derivative of -2 is 0, the derivative of 10x squared y with respect to x.
20xy.
Very good. And we're done. Now, I want you to just kind of notice something here. When you compare the mixed partials with each other, the fxy with the fyx, what do you notice?
They're the same.
The same. Is that always the case? It is if you have a certain condition, which leads us to this theorem, equality of mixed partial derivatives. If you have a function of x and y such that fxy and fyx are both continuous on some open disk R, then for every point in that region R, fxy is a function that will exactly match the fyx function. Pretty cool, huh? Let's do higher order partials where we do third partials. Whoa, what do you mean? Well, if you look here, you see these subscripts, there's 3 of them. Those are third partials. Well, we just did second partials. We're now going to look at third partials. Yeah, but good news, we're not going to do all of them because it would take forever. Like as an example, we're dealing with a function of 3 variables here because they gave it to us. So here's the function of 3 variables. So he would have 3 kids, 3 first partials, right? How many second partials do you think this guy would have?
6.
A little bit more.
9.
9.
Yeah, you're going to have x, 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 fxy, fxz. Then you're going to have fyx, fyy, fyz. And then this is fz over here. I didn't write it very well, fz. So you're going to have fzx, fzy, and fzz. Yeah, you're going to have 9 grandkids. Those are the second partials. So how many third partials do you think you'd have?
27.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. 27, you got it. Third partials. Oh, good thing they're not asking us for all of those because that would take forever and a day to go get. Yuck. But they are asking us for a few of the third partials. So let's just take a look and finish out the problem. Here's the function of 3 variables. They want us to do 2 little mini proofs. First, show that these mixed partials are equivalent, that fxz is going to give you the same thing as fzx. Okay, that's not too hard. And then we're going to show that fxzz is the same as fzxz, which is the same as fzzx. So those guys are going to end up being the same. Now, let's try and do this, and then we'll try to answer a question. Would those be equal to fzxx? We'll discuss that in a moment. So first, let's just do this. Here we go. Fx and fz are the 2. There are 3 first partials, but I don't need the fy to do these little mini proofs because they're not asking me to go get fy. So fx is the derivative of y e to the x with respect to x. I think that's going to be y e to the x. Plus, when I differentiate x times ln z with respect to x, it's just going to look like the constant multiple, ln z. So there's one of the partials. Okay, the other partial, fz, you're going to hold x and y's constant. So what is the derivative of y times e to the x with respect to z?
0.
0.
0. Plus the derivative of x times ln z with respect to z. It's going to be x over z. So now what? Well, if we're going to do the first mini proof, we're going to show that the mixed partials fxz and fzx are equivalent. Okay, so to get fxz, you use fx, which we already got. And you're going to take his partial with respect to z. Okay, so here's fx right here. Oops, still in erase mode. And what is the derivative of fx with respect to z?
One over
Is
z.
it 1 over z?
Just 1 over z. Very good, because the first partial y to the x is 0. So this is going to be 1 over z. Fine. So we got fxz. Now let's go get fzx. So you're going to start with fz and take his derivative with respect to x. So you're going to get fzx. So what's the derivative of x divided by z with respect to x?
1 over z as
1
well.
over z.
And so these are the same. So we just proved this. Yay, success. We just proved that fzx and fxe are the same. Fantastic. So that was part 1. Part 2, go get these third partials. Oh, dear God. Okay, let's look at the first one, fxzz. Well, we already have fxz right here. So fxzz is just look at fxz, which we have, and I'll rewrite it as z to the negative 1, and take the derivative of that with respect to the very last letter, which is z. So that's just going to be negative 1 z to the negative 2, which if I rewrite it with positive exponents looks like that. Fine. So there's fxzz. Now let's get the middle partial, fzxz. Good news, we already have fzx. So fzxz is just telling us to take the fzx and take his derivative with respect to z. But hey, it's the same. So far it looks like the first part of that triple equality, we're good. But now we got to get fzzx. Well, bad news, we don't have the second partial fzz, and you need that before you can get fzzx. So back to second partials. Let's go get fzz. Good news, we already have fz, which is this guy over here. If you take the derivative of fz with respect to z, the x is a constant multiple, and then when you differentiate 1 over z with respect to z, you'll get that. So you're going to get this. Okay, fine. Now you can go get fzzx, because you're going to look at fzz and take the derivative of him with respect to x. Well, that's just going to be negative 1 over z squared. And then these are all the same. So we just proved that all three of those third partials are really the same. Now, what about fzxx? I'm not going to go get fzxx, but this could be a true-false question. Hint, hint. Are you guaranteed that fzxx is always going to be equal to f, say, xzz? And the answer is no. Because when you're saying that mixed partials are equal, this theorem here, please do not get confused. It has to be the same number of derivatives matching. So this fzxx has one derivative where you took with respect to z and 2 with respect to x's, which is very different from xzz, where you took 1 with respect to x and 2 z's. So there's no match there. Now, if they happen to be equal, you got lucky. You know, that was just because the stars were aligned that day. It depends on the function. But you're not guaranteed of that. But you are guaranteed about these three guys, because fxzz is going to give you the same as fzxz, which is the same as fzzx, because all three of those have 2 z's and 1 x. So they're a match. And I'm done.